So we have a confluence, in a sense, of control of structure, whether it's through chemistry, one by one, through assembly with biochemistry, or through engineering that is getting at this place here. There's a convergence towards control at the atomic level to create matter. So, as I mentioned, crystals are entities where you have an understanding of interactions at the atomic level. So, is there a reason, or should we think about, why would we want to potentially control the structures of crystals or engineer the structures of crystals and potentially control properties? So I'll give you two examples that I think illustrate where atomic control, atomic precision, and asserting control is very important. Okay, so here are two compounds, organic molecules, and their crystal structures. Okay, so here on the top we have a molecule known as itraconazole. And so if you're a pharmacist, you're a doctor, what you'll do is you'll prescribe this molecule, itraconazole, as an antifungal drug, okay? And the market cap for this drug currently is about $600 million a year, okay? One problem here with itraconazole is that it's extremely insoluble. Okay, so the solubility is 1 nanogram per mil at around pH of 7 or so. So that's like, chopping off the end of a human hair and throwing in a glass of water. It's really, really difficult to get this compound in solution. And I'll tell you how it's administered commercially. But when you look at the crystal structure here, for this to become soluble, you need to break up the interactions for it to go into solution. And it is not obvious why this molecule is so insoluble, okay? But it is. So you make the molecule, you do a lot of work as a pharmaceutical company, and you think you got it, right? You've got it, it works in a cell, it's doing everything you need to do. It's top of the line in terms of everything you made in the lab. And at the end of the day, it's like dust, okay? It just doesn't dissolve, and you've got trouble. Here's another example. This molecule, it's a little controversial about 20 years ago. Its name is pentacene. And it's called pentacene because it has these 6-membered rings lined up in a row. And pentacene is a molecule that falls in the category of an organic semiconductor. Okay, so I'll get to that a little bit later. But there's this sort of futuristic idea that chemists can make materials that are both flexible and they can support movement of electrons and be useful for sensors and displays, and you can make efficient use of electricity and so on. And this level of flexibility arises because it is an organic molecule. So in your computers, for the most part, you have silicon oxide, which is brittle, it's not flexible, it's a semiconductor. These organics have those other properties. And if you ask your friendly computational chemist that's down the hall, what does it take for this molecule to be the best semiconductor, they will tell you that you want the 6-membered rings situated in a face-to-face sort of geometry. And that's a geometry that supports efficient movement of electrons to support the semiconductor material. However, if you look at the crystal structure, it's not face-to-face. It's actually edge-to-face, where the molecule here is interacting with the other face, sort of like in a T-shaped geometry, okay? So again, you might have made this molecule in the lab, you make this one, and you'll find out it doesn't work as well as you'd like to, but it should, okay? So the question here is, so molecules do what they want at the end of the day when they form crystals, and is this the final story? So can you do anything else here? C'est le fin de l'histoire. Can you do something else to affect that structure, and doing so effectively assert control at the atomic level, okay? Which just gets back to the whole Feynman idea. So you have two options at this point. You can use a computer, and hopefully that computer can predict a molecule that's a semiconductor, and it will have the crystal structure that you want. That'd be great. The other option is to experimentally come up with a way to get the kinds of properties that you want while retaining the structure of the molecule, okay? So how about the computer case? So this is an editorial that was published in Nature in 1988 by John Maddox. And John Maddox was sort of the editor. That was the person that was sort of intertwined into the physical sciences, at least, for Nature at the time. So 1988 gets us a little bit closer to the present. And if you look at the first line here, the first line has the word scandals. Now this is science, right? Why are we using the word scandals in an editorial in Nature? So what he said here is that one of the continuing scandals in the physical sciences is that it remains in general impossible to predict the structure of even the simplest crystalline solids from knowledge of their chemical composition, okay? So what that means is that, again, if you go back to the organic lab analogy, if I take a student, an étudiant from organic chemistry, and that student gives you a molecule on a piece of paper, and I say, let's try to predict the crystal structure of that molecule. It turns out that, at least in 1988, it was generally impossible to do that, okay, to predict the three-dimensional organization of that molecule and then predict the properties, of course, as well. And the reason why that was hard, and it is very hard today, is because we really don't have a great understanding of how shape and electronic structure influence each other at the atomic level. This is similar to the protein folding problem, right? And there's many, many papers published on that in that area. But at the end of the day, it was a huge challenge to predict conformation of a protein. Same thing with the crystal. And here, we're trying to predict the three-dimensional organization of things that are independent, in a sense. So they're not tethered like they are in an actual enzyme. So you could argue that you have another degree of freedom to worry about, okay? So this is a tough problem. And today, there is an annual so-called test that's given out. I think it's annual or biannual, to predict crystal structures. It's the blind crystal structure test. So molecules are sent to different groups, computational groups, and they're challenged to actually predict the structures, turn them in, and then see who's gotten it right. And there's always still some discrepancy between the structure that's been discovered and, what's been determined. So there's still not that, that true certainty. And in fact, a 2-hour drive from here in June, there's going to be the Gordon Conference on Crystal Engineering. And look at the title, Crystals Meet Artificial Intelligence, okay? So this is kind of related to this whole idea of crystal structure prediction and robots and so on and so forth. Okay, so over the last few decades, crystals have found their way into applications, and very promising applications beyond the pharmaceutics and the electronics that I showed you. So here's pharmaceutics, here's electronics. I guess you could argue that the case for Angus, this is a kind of material that would be used for energy storage with the pores and channels that are present in it. So this is an important area today. Catalysis and separations. Crystals are used for those purposes. And many fertilizers are solids as well. They have certain bioavailabilities, and they're crystalline, and it would be good to be able to modify fertilizers to also support agriculture, okay? So these are some areas that currently are representing major technological and I would argue societal challenges. And it turns out that these challenges are also part of the priorities of Canada. Okay, so here are some examples of science, technology, and innovation priorities put out by the Government of Canada. So healthy Canadians, pharmaceutics, sustainable food systems, agriculture, clean and resource-rich Canada, that's separations. Technologically advanced, you could argue, is electronic media. And these kinds of items are also part of the United Nations Sustainable Development Goals as well, okay? So they're all kind of intertwined. And as I get to the end of my talk, I also want to show you that the University of Sherbrooke, again, is really well situated in the context of crystal engineering. And so on the campus, we have the IPS for drug development. We have the 3IT for electronics. And then we have this institute for computation. So they all tie in to a lot of challenges as part of crystal engineering. Okay, so again, these are some important areas. And then if you dial time back about 2 decades from today, I would argue there's a period, if you go back to the concept of history here, there was a period in which I would say there was an important trigger for crystal engineering, okay? And it's related to pharmaceutics. So if you go to about 2003, now remember the idea here is that we have a dead end, and computers might work, and it's an important area called crystal structure prediction, or we can do this experimentally. So here's our friend itraconazole. You'll remember that I said it's very water insoluble. It's at the nanogram per mil level. And so this was a paper published in the Journal of the American Chemical Society by a group or by a company known as Transform Pharmaceuticals that was located in Lexington, Massachusetts, okay? And what they showed is that you can do something relatively simple to affect the solubility of itraconazole. What you can do here is you take the molecule, you make use of the fact that it is somewhat soluble, and you co-crystallize it with another molecule. And so here are the examples of molecules, fumaric acid, succinic acid, tartaric acid. These are compounds that have this group here, known as a carboxylic acid. And what they discovered is that when you take itraconazole and you combine it with those acids, the molecules will combine to form a new crystal lattice, which is called a co-crystal, okay? So if, again, you're interested in protein crystallography and you want to get the structure of a protein, what you would often do is you crystallize the protein with another molecule to form a co-crystal, right? So this is the same process. Itraconazole is co-crystallized with the carboxylic acid. This is the crystal structure. And what was determined is that the co-crystals have solubilities that are actually better than the drug by itself. So here is a time versus basically solubility plot. Here is the dust that I told you about earlier. Crystalline itraconazole, very insoluble. Commercially, what you do is you take itraconazole, you grind it up with a polymer, and that increases the solubility, okay? Polymers cost money, a process costs money, but you do that and you get a relatively soluble material. But the co-crystals here actually are on par with the commercial polymer product. And so if you reflect upon what was done, we didn't affect the structure of itraconazole. What we simply did is we co-crystallized it with another molecule to create a three-dimensional structure. And within the same year, Johnson & Johnson acquired Transform Pharmaceuticals for $230 million, which was partly related to this introduction of a co-crystallization. Around the same time, there was another paper by Mike Zawarodko in the journal ChemCom, 2003, and was also described there were co-crystals of pain medications such as ibuprofen and aspirin. And this was another important paper that showed that if you take these acid molecules, you crystallize them. Now this compound here is not the kind of compound that you'd want to potentially digest, okay, but it was a demonstration that you can also form a co-crystal. For the case of itraconazole, the so-called co-crystal former is something that is acceptable for human consumption, okay? Now you might be wondering, where did the idea of co-crystal come from? And there are two, let's say, pioneers in the area that are important to note. So one here is Gautam Desaraju, who at the time was at Hyderabad, and then Margaret Etter, who is at the University of Minnesota, who also worked in the field of organic solid-state chemistry. So what Desaraju put forward is the idea that if you want to build crystal structures, you can use co-crystals in which you select various groups. So this is a carboxylic acid group here. This is known as a pyridine, and these groups will interact by hydrogen bonds, like the interactions from biochemistry, to form a co-crystal. And then Margaret Etter here also used the idea of a co-crystal to describe or account for the overall topologies of molecules and crystals, okay? So the idea here of combining was a little bit earlier, but then the work of Transform Pharmaceuticals demonstrated some important application that was relevant to drugs and technology. So here is the co-crystal of itraconazole. I just put this little box here to show the itraconazole and then the acid interacting with each other. And then I'm showing a comparison between itraconazole as a structure that I showed earlier. And now here's the use of another molecule to form this co-crystal, which disrupts the packing of itraconazole, how that molecule interacts to form the crystal, and as a result increases the solubility. So we have on the order of a 10-time improvement of solubility of itraconazole using the co-crystal versus the so-called pure compound, okay? So here is the idea that you've done tremendous work, but you just can't go any further, and you can leapfrog over the problem using basically a co-crystal. And so if you look at the area of pharmaceutics, these are examples of how you can develop solid forms of co-crystal or solid forms of drugs. The amorphous form was related to the commercial itraconazole. Molecules can pack in other structures, which are called polymorphs. You can form salts and hydrates. But now co-crystals are an important development that allow you to confront a problem. And another great thing about co-crystals is it provides an opportunity to innovate, okay? So the area of salt formation here to increase solubility is somewhat of a established area. With co-crystals, you can pick the co-former here. You can invent one to actually create a new drug substance. Now, why is that important? Well, it turns out that, you know, to make a co-crystal, you combine the drug and the other molecule, and it might look good on paper. Okay, here's the thing you co-crystallize it with. This is your acid molecule that I showed earlier. This is your drug. You get the structure, but it's not obvious that these kinds of interactions will form. You actually have to do the chemistry in the lab to realize that you'll get a co-crystal. So today, there are several pharmaceutical co-crystals that are currently marketed. And the big one right now is Entresto. So Entresto is what is known as a drug-drug co-crystal. So you have this drug, valsartan, and then you have sacubitril. You combine the two salts of these drugs together, and now you form a new compound or substance that has properties that you will discover are better than the two molecules by themselves. And currently, Entresto is marketed by Novartis, and it's worth about $5 billion annually, okay? So it's an important example of a pharmaceutical co-crystal that has experienced success commercially. And as I mentioned, the preferred way to deliver drugs is through solids, and that area is on the order of $600 to $800 billion annually, okay? And several are currently marketed. If you go back to, if you go back to the example of our Entresto co-crystal, this co-crystal was introduced in 2015, okay? If you go back to 2015, and if you ask the Food and Drug Administration, what is a co-crystal? What they claimed a co-crystal was at that time is something known as a drug product intermediate, okay? So when you make your drug, such as itraconazole, and you form a solid form, that is classified as a drug substance. And drug substances are patentable. Early, co-crystals were not seen as drug substances. They were seen as intermediates. Now, the chemists knew and the material scientists knew that they were actual new compounds. They had their own melting points, bioavailabilities, and so on. So there was a bit of a learning curve necessary to understand what a co-crystal is scientifically, let's say. Okay, it's a good example, actually, for les étudiants, for the interplay between society and science. So, in 2018, only a few years ago, really, the FDA changed the classification of co-crystals. So the FDA said a pharmaceutical co-crystal is a crystalline material, which is a drug substance, basically, composed of two or more different molecules. You have your co-former, and now they reside in the same crystal lattice. And because of that classification, they are now patentable, okay? And they can provide a number of opportunities to improve drugs over conventional solid-state forms of your API. And the great thing is that the drugs are assumed to exhibit bioequivalence as well as their initial forms. So they can be you can bypass, in some cases, clinical trials for those drug molecules. So you can think of ideas now of repurposing, extending patent life, bypass clinical trials, and as I mentioned earlier, developing innovative forms of drugs. And here is a review article that was published in 2022 listing the current marketed co-crystals. So here's Entresto, Stelgrado, Siglentis in 2021, relatively new. And then here's some more of the model examples, going back to the itraconazole example that I mentioned at the beginning. And so here's a quote by the chief scientific officer of Estive, the production of Siglentis. So this innovation is the result of applying a crystallization technology to improve the properties and the pharmacokinetics of APIs. And then clinicians and adult patients have a new treatment option for acute pain management for that drug. This novel co-crystal structure produces a unique pharmacokinetic profile, and that was approved eventually in 2021. Okay, so this was a very kind of interesting history, development, asserting control at the atomic level through a crystalline lattice that finally got us to this point in the terms of pharmaceutics. This is a very quickly a representation of the drug life cycle. So for the students, a patent lasts about 19 or 20 years. And usually the first 12 years or so are used just to develop the actual drug. And then the last 5 or 7 years, you have commercial use. So co-crystals can be used to, create new forms at this end, or they could be implemented at the beginning, where small molecules are actually being studied as drugs towards certain diseases. So it's kind of an interesting area to find yourself in if you're studying pharmaceutical co-crystals. We've done some work in pharmaceutical co-crystals over the years. This is some recent work of ours. So we've looked at thymol. This was a collaboration with AbbVie, naloxone, aspirin, crisaborole. Here's an example where we co-crystallized acetaminophen, which is colorless, with this pyridine dicarboxylic acid, and which is also colorless. And when you combine the two, you get an orange co-crystal, okay, which we think happens because of a phenomenon known as charge transfer. This was done in collaboration with AbbVie, with us. And then I learned a few years ago that there's a small startup in Chicago, Denovix, that is now developing our orange co-crystal as a way to assess the combinatorial development of discovery of co-crystals, actually with a number of other universities. So this was an interesting development. And then more recently, we've published an example of a ternary co-crystal. So you can actually not just be limited to 2 molecules. Here we have this molecule, this one, and this is 5-fluorouracil, which is an anti-cancer drug, also embedded into a so-called ternary co-crystal. The world record right now is 5 or 6 in that area. There are only small examples, small number of examples. Ternary, you'll probably find 100 to 150 examples, but then it just drops off right now. I don't know what it's going to look like in 50 years, but I'm sure it'll be higher. Okay, so getting back to these areas that I mentioned, what I wanted to do, the last part, is to cover developments in these 2 areas, okay? But before I get there, I also wanted to point out some of the work that we've done over the last 20 years or so in co-crystals, which is not on this slide, and that is in the field of synthetic organic chemistry. So it's been our premise, actually back in the year 2000, so around the early days of the pharmaceutical co-crystals, that there are amazing opportunities for chemists to actually make molecules in crystals. So if you think about organic chemists, you normally think about chemistry occurring in the liquid phase, in solution. It turns out that you can actually perform reactions in crystals, but the problem is the same one as the pharmaceutics. You might have a molecule that can react in a crystal, but it doesn't pack in the way that it does react. And so we showed that you can make a molecule come to life in the solid state as far as a chemical reaction goes, and it was this one here. So this is 4,4' bispyridyl ethylene. It has a double bond right here. It is not reactive by itself as a crystal, okay? And I won't get into what the structure looks like, but what we showed is that if you take this molecule and you crystallize it with this one here, which is known as resorcinol, these molecules will assemble by hydrogen bonds such that the double bonds are within about 4 angstroms. And that separation is a perfect distance. I would argue this is atomic control of reactivity, such that it undergoes a 2+2 photodimerization when you shine light on this crystal. And this is also the Chimie, verte, green chemistry, because there's no solvent necessary to form this covalent bond, okay? And we showed that you could do this. Again, I'd say that this is actual atomically precise synthesis. It's synthesis in a crystal. And you think, returning to the ideas of Feynman, that's what he was thinking about. Can you make things at the atomic level? So here, oops, I go backwards. Here we did make this molecule within a crystal itself. And so over the years, what we've shown is that you can make some really interesting molecules that you can't really make otherwise in the liquid phase. This gets back to what Feynman said. You might be able to do things in a different way and make different kinds of structures. So we've made these molecules like lateranes and cubanes and cyclophanes, all through the solid state. This was the picture, or one of the pictures that was at the front of the talk. And so here, whereas you have synthesis in solution, the solid state also provides some very interesting opportunities for synthetic chemists. And this is just a summary of the last 23 years of this research by us. So here we've developed these molecules, we've co-crystallized them with these alkenes, and we form these kinds of products here. This here is what's called a clade. So if you go to biochemistry, there's something you can make called a clade, where you show a relation between structure and function, right? Here we have, these are called template molecules like DNA. They assemble these alkenes and we make some interesting molecules. And a relatively interesting one that we've recently shown we could make is a 4-membered ring here that has 4 different substituents. So again, when you took organic chemistry, you were told that a carbon atom that has 4 groups is called stereogenic, and it would be found in a chiral molecule. Here, we created a cyclobutane that also has 4 different groups. So you can think of it as being stereogenic cyclobutane. And this was the first example in which you were able to install deliberately 4 different groups on a cyclobutane ring in a crystal. The entire crystal just converts to the chiral cyclobutane. It's a racemic mixture that we get, but it allowed us to get this control, atomic control, for the synthesis. And as a side note, there was recently a patent by John Katzenellenbogen at the University of Illinois at Urbana-Champaign that touches upon the fact that tetraaryl cyclobutanes can be used for the treatment of hormone refractory cancer. So what we're making here, whoops, wrong button. What we're making here are what are called tetraaryl cyclobutanes, which suggests that what we're making in the solid state could also find uses as small molecule drugs. Okay, so the last two areas here before we get to the end, electronic media and catalysis. I'm not going to get too deeply into electronic media. You have Professor Vergniori is coming here to talk about topological materials in the future. But, as I mentioned, organic semiconductors is an interesting concept. The whole area, again, 50 billion in 2020. And what we showed in a paper back in 2006 is that you can get the face-to-face stacking of semiconductor molecules in crystals using co-crystals, okay? So these are examples, and I'm not showing this, but these are molecules that are going in this face-to-face geometry. If I was to show you the structures of these by themselves, they're edge-to-face, like pentacene, but we got face-to-face by using these molecules to enforce the face-to-face stacking. And then we recently published a book chapter on that idea. And then in the field of separations, this is another Nature paper editorial, The 7 Chemical Separations to Change the World. Okay, that's a big title. It turns out that 10 to 15% of the world's energy consumption goes into separations. Might speak to the inefficiency of the process. Getting back to Feynman's thought. We've recently shown that you can contribute to this area using our crystals in the solid state. So we did this reaction here where we formed this 4-membered ring, and then we took this molecule here and we ended up crystallizing it in the presence of benzene and thiophene. That's an important separation on that list. And we showed that you can remove thiophene and benzene from each other quite efficiently using the crystallization approach. And this contributes to the idea of desulfurization, this is thiophene, of gasoline. And then just very recently, we just published a paper in which we have performed separations of the so-called BTEX hydrocarbons. So these are molecules known as benzene, toluene, ethylbenzene, and xylenes. So they're important commodity chemicals that go into many of the products that we make. They're notoriously difficult to separate. If you look at the list, one of the 7 challenges is the separation of benzene derivatives from each other. And I won't get into the chemistry here, but we did use a crystal engineering approach to perform that separation as well. Okay, so these are some areas that are important, and I would argue that crystal engineering is making an important contribution to the fundamentals of these areas. And that also brings us to great opportunities. And so as I said at the beginning, the University of Sherbrooke, there are institutes that actually are at the runway of developing applications in the field of crystal engineering. So the CERC here is in green chemistry and sustainability, but crystal engineering itself, as I've shown you, spans to engineering, health sciences, and computation, with the idea that you can also make innovative materials. And at Sherbrooke, we have the health sciences, we have the 3IT, the IQ, computation, electronics, the health sciences. They all are working with infrastructure that relate directly to the kinds of areas that crystal engineering can grow in terms of applications and commercialization. Okay, so at the 3IT, our group is excited about thinking about organic electronics with IPS pharmaceutical co-crystals, introducing solid-state chemistry to IPS, and then at the IQ, hopefully working towards the idea of crystal structure prediction. And so those are those areas there that I mentioned that are related to the university. So applications to commercialization is, we've seen it already with pharmaceutical co-crystals, and other materials created through crystal engineering can be addressed on campus here. Okay, so finally, what is the future? What is the l'avenir? Well, when you place l'argent dans la main de l'étudiant, c'est une grande chance. Oui. So the future, of course, is training and students and contributing to what we're doing in a positive way to make things better. So this is our group currently here, the University of Sherbrooke. This picture's right here, but these are group members that are here, and then we have some on their way. We're very excited about the next step for our research. Another great public university that I came from, this is the group that I had there as well, at Iowa. And some of the research here are coming to, and are already here at Sherbrooke. So finally, over the years, I've been happy to be supported and currently supported by the National Science Foundation for fundamental research. We've had other grants along the way. And then now I have to thank the tri-agency of the CERC for supporting us, and we're looking forward to working with everybody. We're excited, and again, thank you for the opportunity to kind of share with you what we're doing. Thank you for being here. Merci, and I'll be happy to answer any questions, so thank you. Okay. That's right. Yeah. Oh, sure. So the question is, back to the field of pharmacology, how good are we? Is it how good are we to predict the formation of a co-crystal? Okay. So that's an experiment. So the normal thing to do is to look at what's called the Cambridge Structural Database. This is the same as the protein database. And today there's about 2.5 million crystal structures deposited. The idea is to look and see if there are so-called, as Desiraju points out, supramolecular synthons that are there that could help guide what kinds of functional groups you need to identify to co-crystallize with a drug, okay? So how good is that? Well, you know, it's hard to put a number on it, but I would say that combining that with computation in terms of looking at the three-dimensional lattice, I say it's fairly successful, and that's not quantifying, of course. However, what we're good at is making these co-crystal formers, and what we're also good at now is being able to scan potential crystal landscapes through, you know, combinatorial approaches and so on. And we're getting better with the introduction of robots and PXRD analysis and so on. So I'm very optimistic that we're on the right path. Yeah. Yes. Sure. Yeah. So that is being done. In the last, let's call it 3 or 4 years, there have been some papers published in that area. So the idea is to include artificial intelligence, machine learning to help with that in Denver. And absolutely, it's a relatively new area for the crystal engineering. Yeah. 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 That's right. Right. So the question is, it gets back, I think, to the kind of the first question is, what's the rule book? And so we rely upon data, and there are some rules such as, so a hydrogen bond has a hydrogen bond donor, has a hydrogen bond acceptor, right? And there's been work in the last decade to look at assessing the pKa difference between the donor and the acceptor. And if it has a certain value and fits within a certain range, then it's likely you'll get a co-crystal. But again, I realize that's experiment. But I mean, I didn't get into the fact that there are many, many co-formers that have been discovered and are being used. And so I didn't want to send a message here that it's a limited enterprise. There are many, many examples. Thank you. Merci.